Hi, this is Frazier Nyasulu, your instructor for chemistry lab. Lab number 2. Let's talk a little about lab number 2. What I've decided is that I'll do these PowerPoint videos for you to look at. Going from lab number 1 to lab number 2, it's more or less the same thing, but now we want you to do it correctly. We'll now award or penalize points depending on the quality of the results that you're reporting. So this time you should be able to do it as well or better than one Frazier Nyasulu. All right. So, looking at density of, and see if I can pick up a pen here. All right, pointer options, pen. So again, density. Density of what? Solids? Liquids? Yeah, solutions. Solutions are liquids in this case. And we're leaving out gases for obvious reasons. All right, so what measurements do we need? Well, mass and volume. So, objectives: properly make and report. Meaning, gotta make them correctly and write with the right number of significant figures and that kind of thing. So, I'm gonna use the same equipment as before, the electronic mass balance. You know about the tear function right now, and then I'm going to determine the volume of an object depending on its nature. You can determine the object volume in a number of ways. And then, of course, if we're reporting density, we need also to report the temperature. So, density, okay, yeah, what's the difference in density and mass? Well, classically one can say if a pound of gold, a pound of feathers, which is more stuff, well, the feathers will occupy a much greater volume. The difference is that gold is a lot more dense, a lot more mass packed in a smaller volume. All right, so we want to find the density of various substances. So, as you know by now, either through just leaving or through your lecture, density is mass divided by volume. Well, the SI unit for mass is kilogram, but for now we will describe or report our density mass in grams, volume in either centimeters cubed or milliliters. What's the difference between those two of them? They're actually the same volume, but you typically use milliliters if it's a liquid or a solution, and centimeters cubed if it's some solid. All right. So let's see here. So you can take that density is mass over volume and then rearrange it to get density is mass over volume, mass is density times volume, and so on. I'm sure you know how to do those rearrangements. So let's move on. All right. So again, we'll report the temperature as well, just to be legal. So mass. Just like you did last time, you want to use electronic mass balance, so you know about the tear function. I saw a number of students rounding off in their head or deciding what numbers to keep for mass and so on. Record the mass as your mass balance reports. If it says 8.800 grams, write 0.800. Do not write 0.8 alone, because in terms of measurements, those mean different things. And for volume, it depends what we have. If we have a solid, we're going to then determine the dimensions. If it's a regular object, then we can determine the dimensions, and from that be able to calculate the volume. Well, that works very well. And so we can take liquids and determine the volume. Most of them work very well, but it turns out that certain things don't work very well. We are going to use the other pipetter. Let's see if I can get it on the screen. And these work wonderfully for aqueous, for water and aqueous solutions, things dissolved in water. But it turns out if you try and use this for things like gasoline, it doesn't work. The things just drip out. And then also if you try and weigh gasoline, the mass continuously changes. So what do we do? Well, that's another way to determine the density of things that are not going to work very well with an auto pipetter. We are going to determine it using a hydrometer. Now, a hydrometer determines the specific gravity, which is defined as density of substance over density of water divided by density of water. So, if I can get this number by some measurement instrument, the hydrometer, and if I can look up the density of water or determine it, then I can determine the density of the substance. Well, if we measure the temperature in Appendix F, it will tell us what the density of water is at that particular temperature. So in our case then, this item here will be easily known from Appendix F. Temperature, look up the appropriate density, and then you're good. And then in lab, we will determine this, and then we can solve for that. Good. Here's that hydrometer here, and there's a better picture. Let's see, where did I put it? Oh, there it is. This is somewhat of a better picture. So there'll be a cylinder like that, and here's a hydrometer. You put it in, and then you read at the bottom of the meniscus here, and should be able to read to 3 decimal places. 3 decimal places. So again, first decimal point known, second one known, and the third one estimated. All right, let's go back here. So the other thing you'll be doing is making a solution. And then, so we'll make a simple solution. I don't know, sugar in water, salt in water, whatever it is. And then we'll determine the density of those two, the solvent, that is the water alone, and the solution, and then compare the two. How do you make a solution? Well, we want to do it precisely. And so let's determine, let's talk about the concentration unit that's sort of kind of everyday. That is percent mass. And this is mass to mass. So you're talking of mass of a solute and mass of the solvent. Solvent is the one with larger mass. In this case, in our case, it'll be the water. That's a solvent. The solute is what we add to the water. So, percent mass to mass, mass of solute. Note that this is mass not of solvent, but of the solution, times 100. Okay, moving right on. So, you need to make 10% solution 50 grams. You kind of know just from everyday living that 10% 50 grams, that must be 5 grams of solute. Let's do it legally. Aha! Let's write what 10% means. What does 10% mean? In this case, 10 grams sugar over 100 grams of solution. Normally you'd say times 10 to get the 10%. But that's what 10% means. 10 grams sugar per, which is divide by 100 grams of solution. Times, we're doing dimensional analysis here. The units don't just disappear, they must actually cancel out sequentially to give the desired unit. So times 50 grams of solution, and then the units will cancel out. There we go. Gram solution cancel out, and then we get 5 grams sugar. See how it works, where all the units work to give whatever we need. If it's 5 grams sugar, then the amount of water that must be contained in the system is obviously 50 minus 5, which is 45. All right, so you guys will make those solutions, make water alone, make the solution, and then determine the densities of the two of them. Question: what do you expect? Water, 5% sugar, which is supposed to be more dense, or are they supposed to be the same? What's your reason testing for your choice of answer. Anyway, significant figures. Let me remind you how we make measurements. Generally, the rule of thumb is you stretch the measurement system such that that last digit being reported is estimated. And then once you do so, all the values that you've recorded are significant. So you've heard about significant figures. For example, the problem of the zeros. The 1,000 is actually one significant point. Then when you go to 101, because the numbers are embedded, then it becomes 4 significant figures. Here, that's 1 significant figure, 2, 3, and 4 over there. So know how significant figures are classified, and then I'm sure that you guys have done that in your class or before. So you've collected your data, and now you're processing data into results. That means you perform certain calculations on the data. How does that work? And so here's something that you've met in class, or we'll meet shortly. If you're adding or subtracting, you go with the least number of decimal places. Why is that reasonable? The reason is this. If these are measurements, then you're saying there's an error in this second decimal point. Let's say plus or minus 1 in that particular digit. Here, it's plus or minus 1 in the 10th. So consider this. This is a much more significant error than that. 10th position, 100th position. So this error would dwarf that one, and so we go with the least number of decimal places. Same thing with significant figures. So if you're multiplying or dividing, then of course you go with the least number of significant figures. So just apply those 2 rules and you'll be good. All right, so you're going to do density of aluminum. Aluminum. Yes, going to use various measuring routines, measurement of the ruler, and think about again stretching the measurement system until you're estimating the digit. You can call that 1.2. However, if you come to this second one, you have to call it 1.22. The blue there indicates the last estimated digit. Caliper, well, those are what they are, and they are really amazing. So make sure that you zero it appropriately, that you're reading in millimeters in this case, and then in this case it turns out that the calipers are good to 0.01 of a millimeter. So it takes a millimeter, which is divides it 100-fold. And so again, the last digit there is the one that's estimated. And so you do some cylindrical rods, measure the dimensions, and then they calculate the volume. But what happens when you have something that's irregular? Ooh, ha-ha! Fork! What's the volume of the fork? Well, one way to do it is to use a graduated cylinder, measure the volume of the water before, slide the fork or the metal into there, or whatever you want to find the volume of the water will increase, and then the difference is the volume of the object. Auto pipetters. In your lab manual, back of the front page, it says auto pipetters are great, but you can use them so that the results are totally unreliable. Unreliable. That's not good. And I'm quoting somebody there, Mike May. So, what are we going to do? We don't want to use something that generates total unreliability, for sure. Well, it turns out that just by following certain rules, you can go from totally unreliable to totally reliable. Demonstrated this many times to various people. So do it. Let's see. I don't know. This little window thing. Let's see if I can kind of figure out where it is. Aha! Put it where my mouth is. Okay. So here's an auto pipetter. Right. When you press this, you can actually press it. You get to the first resistance point, and if you press on, get to the second. In order to make this work and get reliable results, You gotta go to that first resistance point, always the first one. Then you go into the solution sufficient depth so that you're not pulling up air. And here's an important thing: draw the solution up slowly, right? Then you have your, exactly in this case, 1 milliliter. It shouldn't drip, it shouldn't do anything. So again, and then to pump out, doesn't matter, you can pump out a number of times until you get everything out. So here's the deal. For total reliable results using auto pipetters, check that the volume there is correct, because it's a variable volume. So if you're putting in 1 and this is set at 0.7, not gonna work. So check that. In this case, it's 1,000 microliters showing there. Get to the, come on, it's easy. First resistance point, put it in your solution, drop the solution slowly, 1, 2, 3, okay? Take a second or two to make, afterwards, to make sure that the drawing up of the solution is complete, and then dispense. Can you do that? Yes, you can. Total reliability. Moving right on. So you make your sugar solution. Gotta figure out, in this case, 30 grams. Figure out the mass that you need. Sure, many of you can do that in your head. Put that in a beaker. Then add water until you get 30 grams of total. Then mix the solution. To mix the solution, follow the guidelines. There's a reason why doing things a certain way. Put that little stir-bar thing in a beaker with the sugar and the water, and stir. Don't use like a teaspoon or whatever it is. Nah, stir-bar on the magnetic stirrer, right? And then you guys will determine the density of the water and this, and then with that, figure out whether the density of the water is actually equal to the density of the solution. Okay. For specific gravity, these things are in the hood. As I said before, read the specific gravity to 3 decimal places. Take your time, and then look up the density of the water in the table, Appendix F, and then do the density of the substance. That's it for this lab. Then, of course, you do all your calculations, talk it out, reason it out. You can learn a lot from each other, but no copying. No cell phones allowed, so people are not copying from previous students. I don't know. So, you have me, you have your TA, you have your lab mates. That's all you need. Talk to us, talk to him, her, and together we'll figure it out. That's part of learning. After you're done, oh, by the way, West, all solutions can go down in the drain, drain today, just with a bit of water. Clean up your station when you're done. And this is important: retain the equipment in the original place. Check somewhere, it's Appendix D or something like that. They'll tell you what is supposed to be in the data logger box. Take a look at that and make sure that that's what you have. Nothing extras from other boxes or other places, because then the next group that comes is in trouble. They can't find whatever they need. So again, check the equipment and make sure that each data logger box has a full complement of what is supposed to be there. Be safe, goggles at all times, lab coat, have fun, learn. See you next time.